So good morning, good afternoon, good evening to everyone. I'm Riccardo Patriarca from Sapienza University of Rome in Italy, and it is with great pleasure that I can introduce you to this webinar today, which has been co-organized jointly by the International Economics Association, specifically the Resilience Engineering Technical Committee and the Resilience Engineering Association. So this webinar is some of the results to collaboration, to join efforts in improving and developing the management of resilience in complex systems. So we'll look for methods, techniques, practical experiences in a variety of sectors and systems, such as healthcare, critical infrastructures, energy, critical digital services, transportation, automation, emergency response. So in particular today, we're going to host a webinar on the usage of network theory and network science for modeling structure and dynamics of socio-technical systems. I don't want to invest much word or spend much words on that, because today we have a leading expert in the field, and especially Dr. Oriol Artime, who is currently a postdoctoral researcher at Bruno Kessler Foundation. Dr. Artime holds a PhD in physics and from an institution in Spain, and he has worked on different classification problems and modeling problems, all linked to network science. So, you know, this is one of that multidisciplinary or even cross-cutting approaches we really want to emphasize on in both association. And we truly believe that this could be a relevant aspect for our field. You know, this kind of cross-cutting approaches or multidisciplinary efforts has been widely recognized by many experts in the field. And today, let me mention Professor Richard Cook, who peacefully died at home last month on the 31st of August, 2022. So for those of you who know Dr. Cook and Professor Cook, I mean, there won't be many words necessary, but I want just to, you know, mention him as an excellent person, an excellent researcher. He was a polymath who excelled in multiple careers and usually simultaneously. So this kind of cross-cutting approach is also aligned with what Richard has done during his career. I'll put in the chat a link for you to have a look at his astonishing career and his brilliant personality. Before leaving the floor to Oriol, I want to just stress the fact that at the end of the webinar, you will be asked as an option to give your feedback on the webinar itself, on the presentation, and on the other technical aspects. So it will be much welcome if you could fulfill that kind of survey. Without further ado, I leave the floor to Dr. Artime, and will open his presentation. Just finally recalling you that there are two options to write questions. You can write them in the chat, or even better, in the question and answer. Or at the end of the webinar, you can switch on your mic and ask the question directly. So the floor is yours, Oriol.
Okay, so thank you, Riccardo. So hi everyone, I'm Oriol Artime, and as Riccardo was saying, I'm a physicist working in northern Italy in Bruno Kessler Foundation. And I would like to start by thanking the organizers for giving me the opportunity to give this seminar for the invitation. And while preparing these slides, I assume that there will be no knowledge at all on network science or network theory. So I thought about this seminar as kind of a very introductory one. we will go from the most basic concepts to a couple of more advanced topics at the end. So here is the outline of the seminar. First, I will give a super general introduction. I will mention some empirical systems where that we can simulate as networks. And then I will move to talk a little bit how can we characterize the topology of these networks. And finally, I will mention a couple of examples of what is robustness and resilience and how we assess them within network science. So in front of the question, what is a network? We have many answers, but an intuitive one is just a system that have nodes and links. And we might ask, okay, what type of empirical system can be described as nodes and links? Well, we have many. For example, we have transportation systems. Here I'm showing a network, air transportation network, where nodes are airports, and there is a direct link between these airports if there is a route operated by some airline company. But at another scale, we also have transportation systems, for example, at the city scale, and the multimodal urban public transport. Here I'm showing the example of London, where we have bus with the stations, metro with the stations, and rail. We have also networks in systems that can come from communication networks. Here I'm showing this figure from this work down here, where the authors of the work had information about a mobile phone company in Belgium, and had information about the users and who was calling whom. So what they did was to cluster these users in a sort of groups or communities, and this is what we are seeing here. And they also had information about the predominant language on that group. So we see that representing this system as a network, we gain information on, for example, on how the society is segregated. Here, red means French and green means Dutch. And we see that both communities are quite segregated, are mixed community in the middle that speaks both language. So we can have a sociolinguistical insight from this. Also, we have networks in things related to critical infrastructure, for example, in the power grid, where the nodes are power stations and the links are power lines that distribute this electricity or this power. Or also the internet, where we have routers and computers, and then we have connections between these that are optical fibers or wireless connections. A final example that I want to mention here in the introduction are social networks also. You know that we can have online social networks, but also offline social networks. As here is what I'm showing. These social networks, offline social network, come from a health study where we have many information. You can see that networks here visually, but also we have the tools to mathematically encode this information. We can encode many information in the network. Here, nodes are people whose border color denote their gender, and their interior color denote the obesity status, and the link color between the nodes, between the people, represent the relationship type. So at this point, we can ask, why do we care about networks? First of all, because it's a very general and flexible representation of any interconnected system. And they provide very interesting questions. Some of them are from a fundamental point of view, like more interesting to mathematicians, physicists, or computer scientists. But also with networks, we have a large body of applications in many different areas, like engineering, infrastructures, cellular molecular biology, medicine, sociology, urbanism, economy, etc. And they offer some understanding on the systems where they describe. For example, they offer understanding on some topological characterization of the system by, for example, ranking the nodes ranking by the nodes by importance. They can, for example, detect communities that can be useful later to better understand our system. If our system is incomplete, we can have link prediction. But also they offer understanding on some dynamical features that happen on the network, for example, the cascade spreading or the search optimization, but also dynamical features of the network. We know that networks are not static, but dynamic, and they grow, they shrink, they even might collapse. So we might be interested on how are these processes, right? And finally, they offer understanding on the interplay between topology and dynamics, as here is where robustness and resilience are placed. So entering in the part of the topology of the networks, how we characterize it, one of the main ways to, the simplest one, I would say, is what is called the adjacency matrix, which is a matrix, the dimension n times n, whose elements are 1 if nodes I and j are connected and are 0 otherwise. See, for example, this is a simple example where we have 4 nodes. So our adjacency matrix is 4 by 4. We can imagine that in front of each row, there is a label of the node 1, 2, 3, 4. And at the beginning of each column, there are also the labels. And for example, 1 and 4 are connected. So in row 1, column 4, we placed 1, meaning that they are connected. And since this is an undirected network, meaning that the links do not have a direction, then it's a symmetric matrix, and we also place a 1 in row 4, column 1. And we do this for all the links, and we see that this graphical representation can be encoded in a matrix. For directed networks where the links have direction, we also do that. For example, here 1 is connected to 4. So here we have the origin, here we have the destination. We place a link in row 1, sorry, we place a number 1 in row 1, column 4. And we do that, and we see that we can go easily from the matrix to the graphical representation and back. And this representation of a network is very useful for math, because at the end, this is a matrix. We have linear algebra. We know how to use linear algebra, so we can prove many results using that, but it's very memory inefficient in the sense that we need of the order of n to the square bytes to encode this matrix in the computer. So we would like to have something more memory efficient, especially when we're working in computers. And for this, we have the adjacency list, which is kind of a two-dimensional array with a changing length for each label, for each row. And the length of for the length of each label would be the number of neighbors that the node has. For example, here we have node 1 has 2 neighbors, nodes 3 and 4. So we write 1 and 3 and 4. Now node 2 doesn't have neighbors, so we don't write anything. Node 3 has neighbor 1 and 4, so we write 4 and 1. And so on and so forth. And this is not very useful for math, but it's memory efficient. Here we have we need a memory of the order of the number of links. This m is the number of links, which usually for sparse networks we have that the number of links is much smaller than the number of nodes to the square. And there are some basic quantities that we want to compute and we want to characterize. One of them, I would say that it's the most important one, is the degree, which is the number of connections that each node has. For example, in this sketch that I was showing you, in the undirected network, node 1 has degree 2 because it has 2 connections, and node 3 have 1 degree. And of course, this we can compute it visually, but when networks are large, we cannot go to go and check visually what is the degree of the nodes. But from the adjacency matrix, we have that the degree of a certain node I, which remember, not I, it's the label of the row, it's equal to the sum of the entries of that row. And for directed networks, we have two types of degrees. One, what was called the in degree, which are the connections, if I'm a node, the connections that are entering towards me, and the out degree, that are the connections that are leaving me. And here we can compute the in degree in a directed network as the sum over a row, and the out degree as the sum over the column. Okay. And we might ask, okay, can we have some statistics on the degree? Of course, it would be trivial to compute the mean degree, which is just the mean number of connections that my nodes have in the network. And we could go on and compute higher moments of the degree. For example, the second moment, so we can compute the standard deviation, third moment, but also we can compute the entire distribution, the degree distribution, and it's computed in this way. So here, nk means the number of nodes in my network that have degree k, have k number of connections divided by the total number of nodes in my network. And there are some properties of this degree distribution. First of all, it's a probability mass function, meaning that all its elements sum 1, and can be interpreted also in the following way. In the sense that if we pick a node uniformly at random in our network, and this node will have degree k with a probability p of k. And also the functional form that the degree distribution have give us a lot of information. Gives us information about how the connections are distributed in my system, but also how the system could behave when some dynamical processes are happening on it, but also how this system, just by looking at the degree distribution, we have a kind of proxy to understand how we'll respond to some perturbations in order to assess the robustness and the resilience of the system. Here I'm showing some examples of degree distributions that I will discuss with more detail later on, but from top to bottom, we go from very homogeneous degree distribution, very homogeneous system, to very heterogeneous one. The most homogeneous one is the one where the degree distribution it's picked at one value. This is the Kronecker delta, meaning that only nodes with degree k prime are present in the network. All nodes have the same degree. This would be true for networks that are lattices, that are complete graph, meaning that all nodes are connected to everyone, but also random regular graphs, which are networks that do not have a spatial structure like lattices, but anyway, all nodes have the same number of connections. We have a system that is a bit more on heterogeneous, what's called R-training, where the degree distribution is a Poisson distribution with a well-defined mean value. And the most heterogeneous ones are what's called scale-free networks, where the degree distribution behaves as a power law. And you might know that depending on the exponent of this power law, the moments of the distribution might exist or not. So this is the case of the most extreme heterogeneous system. And as we will see, most empirical systems are scale-free. Some other quantities that we use to characterize networks are what is called the clustering, which gives an idea of how clustered or how compact is if I'm a node, my neighborhood, or if I'm a network, how clustered is the connections that are in the network. We can define it at different levels. At a node level, it's just the ratio between the number of pairs of neighbors of a certain node I, that would be the clustering of that node I, the number of pairs of neighbors that are connected between all the possible pair of networks that the pair of neighbors that node I would have. And from this, we can compute the average by averaging this individual quantity, or we could compute another metric directly from a network-wide perspective, which it would be the number of connected triangles, of closed triangles, divided by the number of connected triples, where a triple is any triad of nodes U, V, and W that are joined with the links U and V and V and W, but we don't need the U, W, so we don't need to close the triangle to have a triple. And here is more or less the idea behind clustering, right? If my neighbors, this node, my neighbors are not connected between them, I will have a low clustering. If my neighbors have also connections between them, I will have a large clustering. Another metric that we have is what is called the average shortest path length, which gives an idea of how two randomly selected nodes, how far away they are from each other. And this is conceptually very simple. So let's take that the distance between two nodes can be counted as the number of links that we have to cross to arrive from one to the other. And we can compute between these two nodes, we can compute the shortest path to go from I to J. So we can focus on a certain node I, and we have the average shortest path of this node I as the mean value of the shortest path between I and all the nodes of the network. So this is again a quantity that is defined at the level of nodes. We can compute this at the level of the network just by averaging these quantities over all nodes, which would be this formula here. We have other quantities that I don't want to spend time on them, but I'm mentioning them here. We have quantities related to ranking nodes. For example, what we call the centralities. Note that networks might have topological correlations. For example, nodes with high degree might be a tendency to be connected to nodes with high degree also, or the other way around. High degree nodes connect to low degree nodes. This is called associativity, and we can measure them. And also we have, for example, quantities related to quantify the level of communities that we have in our network, or mesoscale structures that are called motifs. So now let me say a few words about different network models that we have. I'm going to discuss these ones, which can be divided between models that have fixed fixed number of nodes, and models that have a variable number of nodes. So let me start with this Erdo-Freni graph that is maybe the most famous network because it has been studied since 60 years ago by mathematicians, which is defined as following. We just take n number of nodes and we connect each pair of nodes independently with a certain probability p. And this network have many properties that are nice to study it from the mathematical point of view. For example, we can compute the mean number of links in the network, just the total number of possible connections somehow normalized by the probability p of existence of the link. We have the mean degree, which again it's the total number of connections that a node might have normalized by this probability. The degree distribution in this case can be computed exactly, which is a binomial distribution. And as you might know, this binomial distribution can be approximated by a Poisson distribution in certain limits, which is given by this function here. The average shortest path grows, have this scaling, grows very slowly as a logarithm of the number of nodes. And the clustering here goes as this, the mean degree divided by n. Meaning that for a large system, we will have a clustering that tends to 0. And this, when we compare to empirical networks, we know that this is not true. We know that even though we have, let's say, our social network, or imagine the world population, we are many people in this world, so N is huge. But anyway, we know that we have some closure of connections around in our inner social networks, let's say in our family, in our friends. So when we go and check what are the values of the metrics that I talked before, we see that this scaling, the average shortest path grows with a logarithm of n, more or less holds for empirical networks, but this one doesn't hold. And we realized this when we started having data about networks, that it was not so long ago. Before, mathematicians were working about this, but they were not caring about if these were representing real systems. When we had information about real systems, then we needed to rethink all these models. And one of the first attempts to do that was the model proposed by Batz and Strogatz in a seminal paper in Nature more than 20 years ago. That was, if you want, a way or an algorithm to create networks that have a high clustering and a relatively small average path length. And it was like it follows. We have a regular network, and with certain probability Q that we can tune from 0 to 1, we go to every link and we rewire that link to another node. And you can see that when we have no rewires, we have a regular structure with a high clustering, because the neighbors of a node are also connected between them. And we also have a large average path length, meaning that to go from here to here, we need lots of steps. On the contrary, if we rewire all the links, we end up in a situation where we have an orthorhomony. And what Watts and Strogatz find out is that there is a regime that they call a small world for intermediate values of this Q, this rewiring parameter, that we have a high clustering and a small average path length. Here, P is this Q that I mentioned here. So we had a way to generate networks that were reproducing some empirical features. So, okay, now we can say, okay, with the clustering coefficient and the average path length, what happens with the degree distribution of real networks? Actually, if we go to check the degree distributions, we see, as I was saying, that we have signatures of very broad distributions that span several orders of magnitude. Here, note that these are a logarithmic scale. Here I'm showing the degree distribution of different empirical systems, the internet, a network of protein interactions, email exchange, the citations between scientists. And I'm showing here the the Poisson distribution for that network, the Poisson distribution with the mean degree of that degree distribution. And we see that the mean degree the Poisson distribution do not fit well or do not capture well the features of this distribution. So in front of this, what happened? So Barabasi and Albert, in another seminal paper in 1999 in Science, proposed a model to generate scale-free networks, to generate networks that have this power law degree distribution. And it's a pretty simple model, I would say. And these are the steps. Initially, we have a complete graph, meaning that we have a bunch of nodes that are all connected between them. And at each time step, we add a node that creates M links to the existing nodes, according with a certain probability that it's no longer independent of the degree of the nodes as in the orthorhomony, but is proportional to the degree of the node that I'm trying to connect. So in a way, we can say that there is a preferential attachment, or in other words, what is known as the rich get richer effect. And we keep iterating this, and we are able to reproduce this empirical feature of networks through this model. Analytically, so with the math, you can show that indeed the degree distribution falls as a power law with degree -3. And there are many variations of this model to have degree exponents that vary between 2 and infinity practically. Again, here is I'm showing a plot to a sketch to show the main differences between a Poisson degree distribution and a power law. A Poisson degree distribution, it's more or less centered around a mean value, and the tail falls as an exponential. And for a power law, we have but we have a non-null probabilities. We have enough probability to observe very well-connected nodes in our system, what we call the hubs. And here would be 2 sketches of a Poisson degree distribution that is more or less homogeneous, and here scale-free or a power law network where we have nodes that are very well connected and lots of nodes that have very few connections. Finally, I want to discuss what is the configurational model, which is an algorithm to create networks with predefined degree distributions. For this, we have a degree distribution that it's whatever we want. It has to be normalized, of course, and extract n numbers from that degree distribution. And we assign these n numbers to the nodes. Here, see, for example, here we have extracted 4, 7, 1, 4, 5, 2, 5. And this algorithm, what it does is to pair the stubs of these nodes between them, avoiding self-loops. Self-loop is a link that starts and finishes in the same node, and also avoiding multi-edges. And we do this, and this algorithm allows us to create what is called maximally random networks, and that do not have correlations as far as the maximum degree is smaller than this quantity and the square root of the number of nodes. And this is very useful to create networks with the topological properties in the degree distribution that we want. Here, just a summary of some of the things that I presented to quantify average path length in the different types of networks, and the clustering coefficient and the degree distribution. I would say that degree distribution is the most important one, and what it will appear in the rest of the talk. And to close this section, we might ask why network models are important. Are important for several reasons. First of all, because they offer plausible explanations to reproduce properties of empirical networks. So we can, with this, we can unveil hidden organization principles of our network. Also, they provide baselines for testing algorithms, for example, algorithms to test community detection or link prediction. And they are very useful to reveal the role played by different topological properties on the evolution of different dynamical models running on top of the network. To close, I mean, this is the last part of the seminar. I would like to close by mentioning a couple of examples that will be percolation and cascade spreading, and how to assess robustness in these cases. And for the rest of the seminar, we're going to focus on what we call errors and attacks in the network. Yeah, so this is what I said in the previous slide. We have, as I was saying, errors that they might be seen as random or unpredictable failures that happen in my network, or attacks. That attacks are interventions in my network that have some information about the network. They need some global knowledge about them. And there are different types of responses on my network. One, it might be static, so like links or nodes are affected, and then we see what happened when they are removed, let's say. We have some dynamical responses where there is a perturbation, and that perturbation evolves via first neighbors. That would be local propagation. And there is also non-local propagation that I think it's very interesting, where we have a failure happening, a failure and attack in a network, and that information propagates non-locally through the system, meaning that if a node fails in a part of the network, the next failure might happen far away from that node. So let's begin with percolation. Percolation, it's a very simple process. Percolation is a process where we take an interconnected system, we remove a fraction of the individual units of the systems, that can be the nodes or can be the links, and we compute different statistical and geometrical properties of the system that remains. So note that here that we are in the static regime of responses. You might ask, okay, this is a very simple process. Why do we care about it? Well, first of all, it has a very, I would say, fundamental interest. And for those, I don't want to spend time for this, but just have in mind that this is what we call the simplest model for a phase transition. Phase transition is like, for example, when we have a system that goes from, well, when we have a really abrupt change of behavior depending on a parameter. This percolation is a toy model for many phenomena, and it's relatively simple to do some mathematics with this model, and also the computational treatment is relatively easy. And it's a first proxy to assess network robustness, because we say, okay, for a network to be functional, what we need for sure is that it needs to be connected. If we remove some parts of the network and the network breaks apart, then we know that the system will be no functional. So yeah, this is percolation. As I was mentioning, we take out some parts of the system, and we have different protocols to remove the nodes of the system. We have classical percolation, where the nodes or the links are uniformly picked at random. We have different topological descriptors that can be used to rank the nodes according to their importance in the topological descriptor, for example, the degree. We rank the nodes from highest to lower, and we start removing the ones with highest degree. And we also could use removing protocols that depend on non-topological features. And we will see an example of this later on. So we work with several assumptions. The assumptions that we work here, at least in this slide, but this can be generalized, that we have an uncorrelated network, meaning that there are no mesoscale structures, there are no communities, etc. It is unweighted, so there are no weights defined on the links. It's undirected, and the goal is to find the size of the largest component as a function of these copulation probabilities, the fraction of nodes or links that I will remove, and as a function of the parameters of the degree distribution. And I don't want to spend time through the questions, but this is just for you to know that we can actually compute this, where S is the size of the largest component, can be written as a function of this copulation probability and the degree distribution in this way. Depends on U. The U it's given by this equation down here, and we can also compute the critical point. The critical point is where the size of the largest component, which is here, it's here in the vertical axis. Here F is the copulation probability. The critical point is where this becomes 0. And we see that when here on the top plot, I'm showing an Erdos-Renyi for link and node removal, and here for a scale-free network for different values of exponent. And we see that the behavior is quite different, especially when the degree of the exponent or the exponent of the degree distribution is low, that we approach one in a very smooth way. We have also, now this was for random failures, so we don't have information on where the failures happen, but also, as I was saying, they are degree-dependent protocols. Useful protocol or very used protocol is the one where we remove the hubs. So we set a threshold, K0, and we remove all the nodes that are above that threshold. Again, we can do some math here, and we can compute the size of the largest component as a function of this threshold, and we see that the theory and the theory that is a solid line and the markers that come from the simulations match very well. So the theory match very well the simulations. And again, we see that for a scale-free network, we need let's say it's from the other way around. If we remove some nodes, so we go from right to left in this plot, we need to remove very few nodes to actually break the network, meaning that the scale-free networks, because here I'm targeting hubs, I'm targeting nodes with high degree, and they are very important in scale-free networks. We find that scale-free networks are really weak against targeted attacks. Actually, they should display what is called the robust yet fragile properties. Here I'm showing the diameter of the network, so somehow a measure of the distance, the maximum distance between two nodes, and the changes of this diameter as a function of the fraction of nodes that are removed. And we see that for an Erdos-Renyi, when there is a failure or attack meaning I'm targeting the nodes with high degree, the diameter almost doesn't change. But a scale-free network, when we attack it blindly, we don't have information, we have random attacks, the diameter doesn't change almost at all. But when we attack it, the network really feels that attack. And if we go to the internet or the World Wide Web, we see that this robust yet fragile property, depending on the type of attack that we are implementing on a network, also holds in empirical settings. Yeah, what happens if we want to dismantle, we want to attack the network using non-topological features? We can also do theory for that. Here I'm showing two empirical examples where there is a correlation between features and degree. On the left, we have Wikipedia articles where each here we computed. We have the network. Each node is an article, and the links are the hyperlinks between articles. And we compute the number of single editors that have edited each article, and we see that there is a positive correlation between the degree and this feature or the metadata. Of course, the metadata can be very different from one system to another. And also Twitter. Here we took 2 weeks time window during the pandemic, and we computed the number of fake news shared by users within that 2 weeks time window. And here the degree, it's the number of followers that Twitter user had, and we find this negative correlation. So we might ask, okay, I would like to see what happens in my system if I remove from the network, from let's say Wikipedia, remove the nodes, the articles that do not show an enough level of collaborative process. Or in Twitter, we want to remove we can remove here would be to ban users. We want to ban the users that share lots of fake news, but also they are more or less social prominent. So we don't care about the nodes that have very few connections, very few, that their degree is low. So we have a theory for interventions that take into account the degree and the feature. And again, we can write the size of the largest component as a function of the occupation probability that now will depend on the degree and the features of the node, and as a function of the joint degree feature distribution. And yeah, we can write it like this. I don't want to spend time on this. We can find that for this, again, the theory and the simulations match very well. And in the case where we take into account features, for example, here I'm showing where an example where the features and the degrees are correlated in this way, positively correlated and negatively correlated. We see that that the largest component behave also in a quite non-trivial way. There is a non-monotonous with the as a function of the correlation and the strength, and also as a function of the feature threshold that we choose to remove the nodes. Of course, these metadata tags can be implemented in many empirical settings. Here I showed you the case where the distribution between the degree and the feature is introduced by hand, but also we can have this in we can have features related to spatial networks, where, for example, the feature is the distance of a node to its closest neighbor, or features related to dynamical processes running on top of the network. If you're interested, you can find more details in this work. So a summary about percolation. Percolation, although it's a very simple process, also it's a very flexible framework to study the topological impact that failures and attacks have on my network. When we have homogeneous degree distributions like Erdős-Rényi network, we can say that networks behave like glass. So it's relatively hard when we are attacked them lightly, but when we really attack them with heavy attacks, they dismantle pretty quickly. For heterogeneous degree distributions, networks we can say that are like foam, where random attacks allow to detach many parts, but its core survive significant damage. It's very hard to damage the core and dismantle the network. But when we have degree targeted attacks, there's a networks with homogeneous degree distribution almost do not feel the degree targeted attacks because the variation in the degree is pretty low. And heterogeneous networks, when they are attacked with degree targeted attacks, actually, as we saw, we can quickly destroy them. And for the metadata attacks, I must say that there are no general rules, but we find a non-trivial relation between degree and feature. So we need to be careful how my degrees and my features are correlated in order to implement and interpret these attacks. Finally, I want just to discuss briefly another type of robustness assessment against non-local cascading failures. Cascade failure, we can interpret it as small malfunction that spread across the network, eventually producing system-wide effects. Of course, we need to define how the spreading mechanism occurs. And this spreading mechanism might change from, depending on the system that we want to model. We have spreading mechanisms that are more epidemic-inspired. We have what we call threshold models. We have overload models, etc. And there is a common analytical limitation on all these models, and is that we assume that the failures and the information spread through neighboring contacts. And we might ask if this is always true. Actually, if you go to see the evolution of empirical cascades, for example, the shutdown of airports due to the eruption of this volcano, or the shutdown of power stations in a blackout, we see that the failures do not propagate locally. We have, from time to time, we have non-local jumps. So the question is how to include this non-locality in a model of cascade spreading, having full control of the statistics of the non-local event. And what is the role of the network topology? Yeah.
Oriol, I'm just warning you about the timing because we are running out of it.
Okay.
And, we have like 8 minutes left, but we would like to save some time for questions. So if you can just pass through the main concept of the slides to allocate questions.
Sure. Okay. So for this, just want you to know that you can propose a stochastic model for this, where you have a failure that evolves and from time to time makes the jumps. We can assess the robustness of this through different quantities. For example, the time at which the network dismantles, or if the cascade stops without dismantling the entire system. We have what is the size of the largest component of that. We can do some mathematics. And the mathematics and the simulations match very well. And yeah, let's say that before I presented what we call the robust jet fragile behavior of scale-free networks. Here, in this case, we have a kind of dynamical, robust, and just jet fragile behavior where an avalanche of non-local failures can quickly destroy the giant component, the largest component, if it's able to spread. But if it can stop, then the topology of the network can hinder such diffusion. So the take-home messages of my talk would be two. I would like to say that networks are everywhere, that there are many systems that can be modeled as networks. And regardless their nature, their origins, there are many properties that can be described with a common set of concepts. And the questions and the answers that we have for one type of networks normally are valid for other types of networks. And modeling robustness qualitatively, what we do in network science is we try to isolate topological or dynamical characteristics and determine emergent consequences at the collective level, allowing us to establish clear cause and effect relations. With this, I would like to conclude here. Would you find some introductory references? And I thank you for your attention.
Thank you, Oriol. Sorry to interrupt your speech. I mean,
no, don't worry. I thought it was 1 hour, but anyway, no problem.
It was very detailed. I mean, it's fine that you close with this slide because I can read one of the questions. So it's not the first one that we received, but I think if you can stay a bit longer here, we have one of the attendee asking, I find these methods really interesting, but that's a new topic for me. Where is a good place to start for beginners looking to use these techniques? For example, papers to read. I think the answer could be here. And he's also asking for software to use.
Yeah. So there is about the references. We have, I would say, this first book of Newman. I would say this is the Bible of networks, which is a very long book and very detailed. And the second book about Varavasi, I would say that's more introductory, but also it's written in a very nice way. It's shorter. About, you have plenty of reviews about network, but I would start with these two. And about software, we have plenty of software ready to use. For example, in Python, there's a package called NetworkX. We have in R something called iGraph. I would say that these two are the most two standards to use network to analyze networks through software. Yeah. And
is there any other you would suggest which maybe has less functionality, but it could be even easier to start, something with without hard coding? So is there anything else?
Okay. Yeah, there are some softwares to visualize networks that are called there's one called Gephi, Gephi, I, Gephi, which it's pretty. It has a user. I mean, it has an interface where you can load your network, and you can compute directly there different metrics and visualize it. You can play a little bit. That it's pretty easy to use. You don't have to code anything.
Okay, so there are a few questions popping up. I'll start with another one. And Bruno asks you, can you talk a little longer, or maybe give a reference or something about that, but about topological correlations such as associativity?
Yeah, so of course, again, when we go to check what empirical networks look like, there is a mess there. We have many different types of correlations that are multi-scale, from correlations at the level of the entire network down to correlations at the level of single nodes. Associativity is the tendency of nodes to connect with their neighbors that are similar to them. And you can measure that. There are some papers by Newman at the beginning of the 2000. But anyway, in these books, you will find how to measure that, how to quantify it, how to interpret this, how this is. I would say how to link associativity and robustness. And again, there is few general patterns in empirical systems. We can find associative relations. Again, high degree nodes are connected to high degree nodes. We have these associative relations in certain systems where high degree nodes are mostly connected to low degree nodes. We can find even more complicated correlations.
Yeah, cool. And let's say there is this one by Paul, and he's asking you, are you able to give a quick example of how these techniques can be applied to a socio-technical systems? It's looking for perhaps where human failures are of particular importance. So you mentioned with the Wikipedia example, but is there any other view you can suggest?
I mean, I know, so I'm a physicist, and so I have a bias from physics. So we try to do things as general as possible, okay? There are some theories of network science that allow to quantify robustness when we have a single network, right? Here, what I presented was talking about robustness and properties of the network when we have network models. We have a degree distribution, so we have kind of a family of networks, right? But when you have your network, it's one instance of a network. It's not a family of networks. No? So there are ways, in the same way that I explained here some of the methodology. There are some ways to say, for example, okay, I have my network. Let's say that I want to understand how the topology changes, what happens to the connected components of my network when I remove a certain fraction of the nodes or the links. And you can do that not taking into account the degree distribution, that it's not your network, it's somehow the family that your network belongs to, but taking into account your network. I don't know if that answers the question.
I think it may, but let's try to connect a bit the two domains. So you mentioned like those example of errors or attacks. So one error could be, one person maybe changing their job, so disappearing from their network, and see how the network self-organize or how the properties changes. If I understand that.
Sure. Yeah. Like a particular example could be a power grid. There is a lightning that falls, and then a power line starts getting fire. I mean, starts a fire in the power line, and that somehow propagates, right? That could be a random failure. For the power grid, a targeted attack could be a hacker that have some information about he or she has a ranking about the most important power stations, and he or she decides to hack that power station and shut it down, for example, and that would create a spreading failure that we would like to quantify, for example. That would be an.
I think the challenge here, what Oriol was trying to suggest, is that everything he presented is kind of applicable to anything as long as you can abstract them to nodes and edges and connections. So
exactly
the human connection, technical failure, cyber attacks. So you just need to make some efforts to abstract your domain into a network, and then the computational analytical aspect you presented should remain applicable, right?
Exactly.
So we are now out of time, but I'll quickly ask you two more questions. Unsurprisingly, there are no absolutes here. Are you able to capture representation of the limitation, constraint, and error types as a means of providing further insight? I think that was a question related to the percolation aspects.
Okay, can you repeat the question, please?
Are you able to capture representation of the limitation, constraints, and error types to provide further insight on that?
Well, I mean, of course, there are limitations in this approach, in the sense that all these are mental experiments, you know, and I'm not sure of I'm fully understanding the question, but again, the mental pipeline for these experiments is pretty simple, right? You have a network or a family of networks. You somehow perturb the network by removing with certain protocol some of the elements of the network, and you can control which ones do you want to perturb, and then we compute a bunch of things. You can quantify errors on that, of course. You can find mean behavior. You can compute the fluctuations with respect to this mean behavior of the response of your system.
Yeah. And I think this is linked to the computational efforts we need to put in place. So you show like one example, but this could be done parametrically. So like testing different configuration of errors, different
Exactly.
So to really have a systemic perspective on what are the weak points of our network.
Exactly.
Last one, and then we'll close the webinar. But there is one question about the what is, on your view, the difference between robustness and resilience?
Okay, so my view, it's true that in this seminar and in my community, we use both more or less like synonyms, but of course, for me, robustness is more about a static property. So somehow something happens to the network, and how the network is able to keep functioning as before, even though this something happened, right? Resilience is more about the adaptation for me. You know, you have perturbation in the network that might remove some nodes or not, but I want to understand how the functionality of my network changed to adapt to that failure or that attack. Where in robustness, I don't expect a change of functionality, let's say.
Yeah,
that's my point of view. I guess that you guys are more expert on defining these concepts, but yeah, at least in network theory is how we see this.
I think the large overlapping, maybe their concept could be a bit more refined, but they overall, that's an overlapping with the definition used in our field, let's say. So
nice.
That just proves how I see many potential for, quantifying a bit more the normally soft aspects of resilience engineering. So using this kind of techniques could be a way forward in that sense. And apparently, also by the terminology, there is room for maybe, contaminate one field with the other in some sense. So collaborate on those things.
Yeah.
I mean, since we are a bit out of time, I'll thank again now Oriol for being with us today. It was an excellent lecture, and it's not easy to squeeze in so many technical, analytical, computational aspect in 1 hour, but I think you succeeded quite good, actually quite brilliantly. And I hope it was interesting for our audience today. And I hope again that this could sparkle interest in students, attendees, researchers present today to extend their approaches.
Yeah, so thank you for the invitation, and feel free to drop me an email if you have any question or you want to discuss further these topics. I'm super open to do so. So thank you again.
Thank you again, Oriol. It was a big pleasure. And we look forward to see your developments and possibly collaborate on some of that.
Thank you.
Thank you.